Hello, welcome to my video series of data structures. This is part 4 of module 6, the heap data structure. In this video, we will discuss two merge-efficient heap data structures, the leftist heap and the skew heap. In the previous videos, we introduced the binary heap data structure, a complete binary tree that satisfies the heap order property. In the max heap, each node is greater than or equal to its children. In the min heap, each node is smaller than or equal to its children. We also explored the fundamental heap operations, including construct, find best, insert, delete best, increase key, and decrease key. The heap order property ensures that the best element always locates at the root. This allows the find best operation to run in constant time O1. Other operations rely heavily on the percolation procedure, which restores the heap order property by moving a node up or down in response to insertions, deletions, or key value modifications. The insert, delete best, increase key, and decrease key operations each require a single percolation step, resulting in a time complexity of O log n. On the other hand, the construct operation involves multiple down percolations, leading to an overall time complexity of On. In addition to the above heap operations, there is also a merge operation, which combines two heaps into one. For instance, consider our earlier example of managing a dynamic set of games based on their ratings, where you always play the game with the highest rating. Initially, you owned only an Xbox and used the heap to track your Xbox games. Later, you purchased a PS5 and built a separate heap for your PS5 games. Since you can now play games on both platforms, you need to merge these two heaps into a single heap, allowing you to efficiently identify the highest rated game across both platforms. Computationally, the merge operation takes two heaps and combines them into a single value heap while maintaining the heap order property. How can we efficiently merge two binary heaps, each of size approximately n? An intuitive approach is to insert all elements from one heap into the other, one at a time. Since each insertion takes O log n time, inserting n elements results in an overall time complexity of O n log n. Alternatively, we can concatenate the internal arrays of the two heaps into a single array. Since this array does not necessarily maintain the heap order, we treat it as unsorted. Next, we construct a new heap from this concatenated array from scratch, which can be done in On time. Compared to the previous approach, this approach is more efficient. However, an On time complexity may still be too slow if the merge operation needs to be performed frequently. In this video, we introduce two merge-efficient heaps, the leftist heap and the skew heap, both of which can perform merge operation in O log n time. However, this efficiency comes at a cost. These data structures increase the time complexity of the increase key and decrease key operations to On. The time complexity of the other major heap operations remain unchanged. Both leftist heaps and skew heaps are variations of binary heaps, meaning that each node has at most two children. They also satisfy the heap order property, ensuring that the best data element is always located at the root. However, Unlike traditional binary heaps, both leftist heaps and skew heaps are intentionally unbalanced and are not complete trees. As a result, they cannot be efficiently implemented using arrays. Instead, they must be implemented using nodes and pointers, similar to generic tree-based structures. The leftist heap and skew heap are highly similar, and we will first focus on the leftist heap. Informally, a leftist heap is an unbalanced binary tree, where each node has a deeper left subtree and a shallower right subtree. For example, as shown in the slide, a leftist heap typically leans towards the right, as its left subtrees tend to be deeper than its right subtrees. To define a leftist heap formally, we first introduce the concept of null path length, or NPL. The NPL of a node is the length of the shortest path from that node to a descendant node that has fewer than 2 children. Know that a node with no child is called a leaf node, and a node with only one child is called a unary node. For example, in the heap shown here, the NPL of node A is 1, as the shortest path to a unary node is AC. The NPL of node B is also 1, as it can reach a leaf node D or a unary node E in one step. Finally, the NPL of node C is 0, as it itself is a unary node. Formally, a leftist heap is a binary heap that satisfies the leftist property. For every node, the NPL of its left child is greater than or equal to the NPL of its right child. This property explains why leftist heaps tend to have a deeper left subtree and a shallower right subtree. In the slide, the left heap is a valid leftist heap, and the property holds for every node. However, the right heap violates the leftist property. For example, in the right heap, node I has a left child k with an NPL of 0, while its right child L has an NPL of 1. Therefore, the right heap is not a leftist heap. Now that we have defined the leftist heap, let's explore how it performs the merge operation. To merge two leftist heaps, we recursively perform the following steps. Assuming max heap, we first merge the heap with a smaller root with the right subtree of the heap that has a larger root. After the merge, if the NPL of the right subtree is greater than the NPL of the left subtree, swap the two subtrees. Here, the NPL of the right subtree refers to the NPL of the right child of the root in the merged leftist heap. Let's walk through an example to demonstrate how the merge operation works. We need to merge the two leftist heaps shown here. First, we compare the roots of both heaps. We found that the root of the second heap, node H, is greater than the root of the first heap, node A. According to the merging rule, we merge the first heap with the right subtree of the second heap. As a result, in the next recursive step, we continue merging the yellow components of the two heaps. The gray component of the second heap is temporarily ignored and will be considered after the current recursion returns. We apply the same rule and compare the roots of the two active components. The root of the first heap, node A, is greater than the root of the active component in the second heap, node J. In this case, we merge the active component in the second heap with the right subtree of the first heap. That is, we merge the subtree rooted at node J with the subtree rooted at node C. Again, the gray components remain masked and will be processed when the current recursion returns. In this recursion, since node C is smaller than node J, we merge the subtree rooted at C with the right subtree of node J. At this point, we observe that the right subtree of node J is empty. In this case, we can directly attach the subtree rooted at C as the right subtree of J. The scenario where the right subtree to be merged is empty represents the base case in the recursive merging process. After attaching the subtree rooted at C as the right subtree of node J, we check the NPLs of its children. The NPL of J's left child is 0, and the NPL of J's right child is also 0. Therefore, no swap is needed. Since now we have handled the base case of the recursion, we return to the previous recursion level. To complete this upper level recursion, we attach the merged heap as the right subtree of the first heap. After attaching the merged heap, we obtain the yellow heap shown on the left. Next, we check the NPL of its two children and find that both are 2. In this case, no swap is needed, and we can continue returning to the upper recursion level. To complete the final step, we attach the merged heap as the right subtree of node H. After merging the two heaps, we check the NPL of node H's children. The NPL of the left child, I, is 1, and the NPL of the right child, A, is 2. In this case, we swap the two subtrees to restore the leftist property. After swapping the subtrees, we obtain the final merged leftist heap, as shown here. You can verify that both the heap order property and the leftist property are fully satisfied in this merged heap. The two steps in this merge procedure guarantee that the resulting heap remains a valid leftist heap. First, always merging the heap with the smaller root with the right subtree of the larger root ensures that the larger root becomes the new root of the merged heap, preserving the heap order property. Second, swapping the left and right subtrees when necessary ensures that the NPL of the left subtree is always greater than or equal to the NPL of the right subtree, maintaining the leftist property. Now, let's analyze the time complexity of the merge operation. To better understand the analysis, we first need to understand why NPL should be used when defining leftist heap, and how it differs from the tree height. Recall that the tree height is the length of the longest path from the root to a leaf node. On the other hand, the NPL is the length of the shortest path from the root to a leaf or unary node. In a sense, height measures the longest path in a heap, and NPL measures a shorter path in a heap. In a balanced tree, such as a binary heap, all root-to-leaf paths have approximately the same length. In this case, the height and the NPL of the tree differ by at most 1 and essentially refer to the same value. For example, for the binary heap shown here, its height is 2, as indicated by the blue path. Its NPL is 1, as indicated by the red path. Since the tree is balanced, the difference between them is minimal. However, in an unbalanced tree, such as the leftist heap, the height and MPL can differ significantly. For example, the leftist heap shown here has a height of 3, as indicated by the blue path. On the other hand, its MPL is 1, as indicated by the red path. Given the definitions of tree height and MPL, we claim that MPL can better estimate the number of recursive calls involved during the merge process. Consider our previous example of merging two leftist heaps. Let merge st represent the function that merges the leftist heaps rooted at nodes s and t, respectively. During the merge process, the recursive calls include merge AH, merge AJ, and merge CJ. The nodes involved in these recursive calls are marked purple in their respective heaps. Observe that the nodes involved in the recursive calls follow the rightmost path. This is because the merge procedure always attempts to merge the right subtree of one heap with the other heap. Also, observe that at each recursion level, one of the two parameters of the merge function is replaced to its right child. This means that the number of recursive calls is bounded by the total number of rightmost nodes in the two heaps. In our example, those rightmost nodes are highlighted in purple. Since leftist heaps are intentionally unbalanced, their left paths are generally longer than their right paths. As a result, the purple rightmost nodes form shorter paths within the heaps. In addition, the base case of the recursion occurs when one of the heaps being merged has an empty right subtree. This means the recursion terminates upon reaching a leaf node or a unary node. Thus, the path formed by these purple rightmost nodes correspond exactly to the MPLs of the heaps. In other words, compared to tree height, MPL better estimates the number of recursions involved in the merge operation. With a clear understanding of MPL, we can now analyze the time complexity of the merge operation. First, we claim that each recursive step in the merge process completes in constant time. Specifically, in each recursion, we perform the following steps. We compare the root nodes, attach the merged tree, update the MPL values, compare the MPLs, and swap the left and right subtrees if necessary. All of these steps are performed in constant time, O1. Therefore, each recursion step only requires constant time to complete. Second, we claim that the number of recursive calls in the merge operation is upper bounded by the sum of MPLs of the two heaps being merged. We established this claim before when discussing the significance of MPL in defining leftist heaps. Third, we claim that the MPL of a leftist heap is upper bounded by O log n, where n is the size of the heap. By definition, the MPL cannot exceed the shortest root to leaf path in the heap. It follows that the MPL cannot exceed the average root to leaf path in the heap. The average root to leaf path length of a heap can be estimated by assuming that the heap is balanced, where all root to leaf paths have approximately the same length, O log n. In this case, the MPL of a leftist heap cannot exceed the height of the balanced binary tree of the same size, which is O log n. Combining these observations, we conclude that the merge operation can invoke at most O log n recursive calls, and each recursive step completes in constant time O1. Thus, the overall time complexity of the merge operation is O log n. We now present the implementation of a leftist heap. Since a leftist heap is not a complete binary tree, it cannot be implemented using an array like a binary heap. Instead, it must be represented using a tree-based data structure. Each node in a leftist heap stores 4 key pieces of information: the data element, a pointer to the left child, a pointer to the right child, and the MPL of the node. Here is the implementation of the merge procedure. The function merge subtree accepts 2 parameters, mt and st. Mt is the root of the main tree, whose right subtree should be merged. St is the root of the subtree, which will be merged with the right subtree of mt. In line 3, the merge is performed using the function merge, which is a wrapper function for the merge process. Subsequently, the root of the merged tree is assigned to the right child of mt, effectively attaching the merged tree as the right subtree of mt. In lines 4 to 7, the MPLs of mt's children are compared. If the left MPL is smaller than the right MPL, the left and right subtrees are swapped to maintain the leftist property. Finally, in line 8, the MPL of MT is updated based on the merged leftist heap. At last, we implement the merge function, which takes as input the root nodes of the 2 heaps to be merged. This wrapper function compares the 2 roots and decides which heap should serve as the main tree and which should serve as the subtree. It then calls the previously implemented merge subtree function to merge the 2 heaps. After discussing the merge operation for leftist heap, we will proceed to present the other fundamental operations for leftist heap. First, since the heap order property still holds in a leftist heap, the best element is always at the root. This allows the find best operation to run in constant time O1. Second, to insert a new element, we treat it as a single node heap and merged it with the existing heap. Since the merge operation takes O log n time, the insert operation also runs in O log n time. To delete the best element from the leftist heap, we remove the root and then merge its left and right subtrees. As merge takes O log n time, delete best also run in O log n time. Since leftist heaps maintain the heap order property, node value changes caused by increase key and decrease key can also be accommodated using percolation. However, unlike a balanced binary heap, a leftist heap can be highly unbalanced. It means that the height of a leftist heap can be On, as well as the percolation path. As a result, both increase key and decrease key have a worst-case time complexity of O(n). Finally, for the construct operation, we can build a Leftist heap from a set of unsorted elements in O(n) time by performing pairwise merge. Pairwise merging involves recursively combining pairs of heaps until all data elements are incorporated into a single heap. Initially, each element forms its own single element heap. Consider the recursion tree shown here. In the bottom layer, each box represents a single element heap. The first heap contains A, the second contains B, and so on. Next, pairs of single element heaps are merged to form size 2 heaps. For instance, the heap containing A merges with the heap containing B, resulting in a size 2 heap containing both elements A and B. This merging process continues recursively, combining pairs of heaps at each level, until all elements are included in a single heap. In our example, the heap at the root contains all data elements, serving as the final output of the construct operation. Now, let's analyze the time complexity of the pairwise merge strategy. Note that in the Leftist heap, the merge operation can be performed in O log n time. Consequently, constructing a size 2 heap, such as the one containing data elements A and B, requires O log 2 time. Let T denote the actual time spent on constructing a size 2 heap, where T is in O log 2 and thus a constant. Extending this pattern, constructing a size 4 heap requires O log 4 time, which evaluates to T plus 1. Similarly, constructing a size 8 heap requires O log 8 time, which evaluates to T plus 2, and so on. As we ascend one level in the recursion tree, each merge requires one additional step, but the number of merges is reduced by half. Since the heap size doubles at each higher level, the recursion tree has a height of O log n. Denote the recursion tree height as h. In this case, let Ti represent the total effort spent at the ith layer of the recursion tree. Ti can be computed as 2 to the power of I times T plus h minus I. For example, at the 0th layer of the recursion tree, only one merge is required to construct the heap at the root, and this merge takes T plus h time. At the next layer, 2 merges are required, each taking T plus h minus 1 time. This pattern continues as we move down the recursion tree. To determine the overall time complexity, we sum Ti over all recursion tree levels. Notably, this sum follows a structure similar to the time complexity analysis of the binary tree construct operation. In the previous video, we provided the detailed simplification steps and showed that the sum evaluates to On. Thus, the Leftist heap can be constructed from n unsorted data elements in On time. It is important to note that the above analysis does not depend on any property unique to Leftist heaps. It means that for any heap data structure that supports O log n time merge operation, its construct operation can run in linear time O(n). This observation will be referred to when analyzing the construct operation of other merge-efficient heap data structures. Now, we summarize Leftist heap by comparing it with binary heap in this table. In short, the construct, find best, insert, and delete best operations have the same time complexity in both heap data structures. The merge operation is more efficient in a Leftist heap, running in O log n time instead of O(n) in a binary heap. However, the increase key and decrease key operations become slower, whose time complexity is increased to O(n) in a Leftist heap. While Leftist heap optimizes the merge operation, it can no longer be implemented using an array. It means that each node now consumes more space to store two child pointers and the MPL value for that node. In addition, data elements in a Leftist heap are scattered across memory, resulting in slower access time. Hence, a Leftist heap is only preferable when merge operation is performed frequently. The second merge-efficient heap we will discuss in this video is Skew heap. Recall that one drawback of Leftist heaps is that they require additional space and operations to store, update, and compare the MPL values during the merge process. To eliminate this overhead, Skew heaps completely discard the use of MPL information. Instead, they always swap the left and right subtrees during the merge process, without checking any structural properties. Without MPL information, the path formed by the rightmost nodes is no longer guaranteed to be the shortest path in the tree. As a result, we can no longer guarantee a worst-case O log n time complexity for the merge operation. Despite this, it is possible to prove that the amortized time complexity of a series of merge operations remain O log n. Next, we will provide a high-level outline of the time complexity analysis for the Skew heap merge operation. Consider the two heaps shown on the left. In the average case, each of the four subtrees contains approximately 1/4 of the total nodes. Suppose we merge the right heap with the right subtree of the left heap. The resulting merged tree now contains 3/4 of the total nodes. Since the right subtree grows larger, we will likely need to swap subtrees, ensuring the larger tree is placed on the left. This implicitly restores the Leftist heap property, even though Skew heaps do not explicitly check MPL values. In this video, we introduced two merge-efficient heap data structures, Leftist heap and Skew heap. We provided a detailed breakdown of the merge operation and showed that it runs in O log n time. Some fundamental operations in Leftist heaps, such as insert, delete best, and construct, are efficiently implemented using the merge operation. To eliminate the overhead of storing, updating, and comparing the MPLs, Skew heaps discard the MPL information and instead always swap their left and right subtrees during merging. Although Skew heaps no longer guarantee O log n worst-case time complexity for merge, the amortized time complexity remains O log n. Finally, both Leftist heaps and Skew heaps should be implemented using node-based tree structures, which are less efficient than array-based binary heaps in terms of both memory usage and access speed. Hence, these structures should only be used when the merge operation are performed frequently. Thank you for watching, and see you next time.